All right. So yesterday's class we had talked about multi-stage crossbar switches, and we had also talked about simple crossbar switches. Okay. When we were looking at simple crossbar switches, we found out that it is internally non-blocking, but because of the number of cross points increasing a lot, and also the case that suppose there is a failure of one cross point, one input port will be totally blocked. Okay, that corresponding input port will be totally blocked. So that was the reason that we started thinking of something more efficient than a simple crossbar switch. Of course, let me remind you once again, crossbar switches are basically space division switches, the simplest form of space division switches. Now with that, we came up to, okay, let us get to multi-stage crossbar, and we talked about a three-stage crossbar where we had shown where it was shown to you that how to create this multi-stage crossbar, and we finally found out that the multi-stage crossbar actually suffers from internal blocking. Why it would suffer from internal blocking? That is, if the array size that we are considering, that is the size of the second level stages, if that becomes lesser or smaller, in that case there wouldn't be sufficient paths from the input ports to the corresponding output ports. Okay, and that will cause internal blocking. All right, so although the multi-stage crossbar gives lower number of cross points as compared to a simple crossbar switch, it is internally non-blocking, and therefore we need to find some ways out to improve, have an improvement over the multi-stage crossbar. Okay, also for a multi-stage crossbar, at each point, whenever there is an input and it needs to go to the output, in that so the switch controller actually needs to find a path from that particular input port to the particular output port. Okay, so every time there is an input, there should be path search algorithms executed by the switch controller to find out that what is the corresponding output port. We can store the switch schedule, we can store the path in the switch schedule, but it still can have there will be scenarios because the input, we do not have any control on the input as of now. Okay, so that is the problem that we have for multi-stage crossbar switches. And even though it says that it has lesser cross points than crossbar, but still the number of cross points is too large. So that is why Claus uh, found out a way that in which a switch controller can actually behave in a much more efficient way than that of a multi-stage crossbar. Okay, so the biggest challenge for a multi-stage crossbar is actually to find out the value of k, right? So class actually showed that if k is greater or equals to n, that is n being the number or the size of the group or the group size in which your input is divided, right? So if the k is greater or equals to n, specifically if k equals to 2n minus 1, then your switch will become internally non-blocking, and you can actually rearrange, if you can actually rearrange the existing connections whenever there is a new call arriving, in that case also your switch will become essentially non-blocking. Okay, so that's what Claus said, but if you think about it, rearranging connections whenever there is a new call happening, then that becomes pretty complex, right? We cannot think of a scenario that we are actually going to change the connections. Okay, so can we use this principle but still do not change the circuitry? We cannot do that, right? That is something not possible. So can we just emulate whatever this principle is saying in our current scenario, whatever device we are currently having. Okay, so that's what clause said. Now with that, we come up to starting with today's class, where we are talking about time space switching. Okay, so it is using time slot interchange, and it is also using space division switching. Okay, that is what is giving the name, that is time space switching. Okay, now if you remember, when we were using TSI, we were using it just after the sample is arriving out of the multiplexer, right? So as an output of the multiplexer, we get a frame with different samples, and then we use the TSI on that, or basically we enter that sample through a TSI and then send it to the demultiplexer. That's what we had seen when we were talking about TSIs. Okay, so here how can we work that out? So we, in general, the input that we are getting from the crossbar to the crossbar is actually multiplexed input, right? So what is happening here, what can we do here, that the samples that are arriving at these crossbar switches, also please remember crossbar switch is a space division switch, right? So whenever the samples are arriving, if there is a contention between the uh, destination ports, I mean for any input to the destination port, if there is a contention, then what can we do? We can actually delay that using a TSI. Okay, we can delay the sample. So for example, these look at this example that has been given here. So we have 4 input ports, and we have samples arriving at each one of these input ports. Okay, now this input, that is 1, and this one, that is 13, suppose they are intended for the same output port. Okay, so with that, what will happen, 1 and 13, they both will contend. Okay, so with this, what happens if they are following the same path, if they are so contention will happen when, if they follow the same path, or if they are having the same output port, or their paths intersect for some amount of cross points. In that case also there will be contention. Okay, so suppose these two samples, that is 1 and 13, these are contending. So now in that case, what can we do? We can delay samples. How can we do that? We can just move the samples within the frame with the help of a TSI. So that's what is happening here. We are putting a TSI just after the input is arriving. So we have TSIs here, and with this TSI we are simply rearranging this frame. Okay, so in this frame the sample gets interchanged here to the second slot, and then we have this one which is completely kept intact, so that this can move to the corresponding output port. Okay, so now you can see that there is no contention here. Now at the we need to reorder samples with the input line and then switch them to different output lines. Okay, so this is what, or this is how your time space switching will help you if you have output blocking. That means for a given output port, if there is a contention, that means the output port is not available for the corresponding input port. Okay, so in this kind of a scenario, your time space switching will help you out in avoiding that kind of contention. Okay, so this is one way of improvement, where, so if you think about the class network here, you are essentially changing the input in such a way so that their paths are changing. Okay, that's what Klaus was saying, that we need to somehow change the path, right? So here we cannot change the entire circuitry. What we are doing is we are changing the input itself in such a way so that it, the inputs basically take paths which are different from each other at one point of time, so as to avoid contention. Okay, So this is what our time space, this is what our time space switching is doing. Now we will get to another kind of switching, which is known as time space time switching or TST switching. Okay, so this is another way. So if you remember in this one, what we were doing, we were changing the samples, right? We were rearranging. So that means at the output, we will get an out of order sample, right? So can we improve on it? We can have a three-stage crossbar, similar to a three-stage crossbar kind of a scenario, using a time space time switching. Okay, so you can see here that at the input port also you have TSIs, and at the output ports also you have TSIs. Okay, so what is happening? We can flip samples at the input port, and then whatever rearrangement has happened at the input port, that can again be changed at the output port with the help of the TSI which is there. Okay, so with this, what happens? It gives you more flexibility, lowers the call blocking probability. All right, so let us see how it works. So suppose this is the input that you have originally received, which is 4, 3, 2, 1 and 16, 15, 14, 13 in these two particular input ports of the crossbar. Now now we can see, suppose these two inputs, okay, 1, 2 and 13, 14, okay, they are all suppose intended to output port 1. Okay, so in that case, what will happen? There will be contention among all of them. Okay, so we need to change the sample, rearrange the sample. So for that, of course, we have TSIs at the corresponding input ports. So the rearranged sample now becomes something like this. Even for this one, the rearranged sample becomes like this, that is 14, 16, 15, 13. Now with this, the paths have changed at each point of time, and there's no contention. So therefore, they will move to their corresponding output ports. Now at the output ports, again, we know that the path has changed, right? So what do? We use the TSI. Now according to what will we get? So this is the output at the output port 1, right? So what were these were intended, 1, 2 and 13, 14, these were supposed to reach the output port 1. Okay, and these are basically destined for two different trunk groups. One is trunk group A and another is trunk group B. So 1 and 2 are supposed to go to trunk group B, or they are part of trunk group B, and 13 and 14 are part of trunk group A. Okay, so what the TSI here will do, once it receives this kind of a sample, it interchanges that sample, and then again we get this exact ordering that we were looking for. That means you have 1 and 2 which belong to trunk group B, and you have 13 and 14 which belong to trunk group A. Okay, so this is what or this is how your time space time switching works. I hope that this is clear. I'll go to the next part after this. Okay, so far we have assumed that whatever data that is incoming at the input ports, they are all having the same rate. That means the data that is arriving at the input ports is arriving at the same rate. But that does not happen in the real case. In real time, that it may not happen. The rate may not be the same for all input ports. So what do we do if there is heterogeneity in the packet arrival at different input lines? Okay, so for this we can have different ways. We do not have to make very big changes for that. We already know that we can use multiplexers at the input ports just to get the samples in a particular frame so that more number of inputs can be sent. So for that, if your one of the input lines is giving you very slowly some input and another is giving on a probably suitable speed, you can actually use multiplexers to get more and more samples together. Okay, so that is one issue. Another issue that maybe you can ask is that what if the packet size is different? Okay, so we will get to that question, but another point that I'm missing here is that if your input line is too fast than what the switch fabric can actually handle, then you can use a demultiplexer to reduce the amount of input that should enter into the switch. Okay, so this is how we can deal with line heterogeneity. And now let's get to the next one. Okay, I think I made a mistake here when I was talking about the packets. Here we are talking about circuit switches, right? So we are not talking from the point of view of packets here. We are sending as samples. We'll talk about packets for packet switching. Okay, I just made a mistake there. Okay, so all right. So now since you have studied all of this, now you have studied that there are a lot of cross points in case of crossbars, and there are different ways of um, changing this situation by using either multi-stage crossbar or time slot interchanges placed in different input and output ports. Using a combination of both of them, you have studied everything by now. Now it is up to you to make a decision as to there are advantages of crossbars, there are advantages and disadvantages of all the other different variations of switches that we have studied. Now, given all of these advantages and disadvantages, what do you think? Whether having cross points is really expensive for us, but given that crossbars are having a lot of cross points, but they are the simplest ones to work with. Okay, and if you simply put TSIs in different places, then you can use a crossbar. However, again, we will have that same issue that uh, if a cross point is not working, then that input port is completely blocked. Again, you have a solution for that also by changing the path. So there are many things that you can do. So it is up to you. That is, what do you think, that whether cross points are going to be really expensive or not? Okay, which one becomes more expensive, which one becomes less expensive? It becomes to your judgment, and I would like to know about this from you later on. Okay, so think about it as to what do you think about whatever changes have been made and whatever cross points are actually doing, crossbar switches are actually doing with the help of TSIs. So let us get to the next part of this module, and that is for packet switching. Okay, so we know what is packet switching. So it is basically connectionless. We do require headers for each packet in order to send them to their rightful destination, and just having that information attached with them. Now we have studied about ATMs, and for that we have also studied that they are fixed size packets and the destinations are decided by the VCIs. Okay, so if you have ATM switches, then of course those switches will deal with fixed size packets, and they will simply deal with choosing finding out that what is the value of the VCI, and then accordingly take a decision of sending the packet to the corresponding output port. Okay, now when it comes to datagram switches, all right, so datagram switches have to work with variable sized packets, because we are talking about basic packet switching, and here we cannot have, in general, we do not have any constraint on the packet size as such, that whether the packet size will be fixed or whether it will be of variable size. Okay, so datagram switches are mostly having variable size packets, and your entire destination address in terms of IP address is given there. Okay, so whenever the packet will arrive, then the destination address needs to be parsed to find out what is the longest prefix matching, and then you need to match it to find out what is the corresponding output port. So a lot of task comes, which is basically overhead in case of datagram switches. So these datagram switches can have both internal and output blocking. So you might ask me a question as to how it is having internal and output blocking. So think about the scenario that when burst size of packets are incoming, and of course there wouldn't be any space for the particular output port, that is going to cause you internal blocking. And of course output blocking will be there if more than one uh, input ports are intending to send packets to the same output port. Head of line blocking, all of this are part of output blocking, and of course a part of datagram switches. So the blocked packet, now what is the option here? If a packet is blocked, then it has to be either dropped or it needs to be buffered. Okay, so that is the situation that comes around when we are talking about packet switching. Okay, now if we are having blocking, then what can we do? Okay, so these are some solutions, possible solutions that have been given. So one is over provisioning. That means you just make more and more internal links faster than the inputs. Okay, so if your internal link, that is the switch fabric's capacity, is much faster than how fast your inputs or your input line is, so in that case they will transfer the data much faster. Okay, but again this is expensive, and of course it will be a waste of resources when you do not have any bursty traffic at that point. So this is over provisioning. Then we have the other one that we were talking about, that is if you do not want to block a packet, that means if you do not want to drop a packet, you can simply buffer it, and therefore we would need buffers at input and output ports. We have already seen in our basic diagram of routers that we do have buffers at the inputs as well as outputs. Okay, there's another way of dealing with blocking, and that is back pressure. I am sure you might have studied this in congestion control for computer networks, basic computer networks. If not, just the name suggests back pressure means you give out a pressure back so that the input that is coming with that high rate does not come further. Okay, so what happens in back pressure in case of switches? It allows a multi-stage switch fabric to prevent the previous stage from sending any more packets. Any more data. Okay, so this will allow the switch fabric to have very less amount of buffering, because anyways the switch fabric, the next stage is going to inform that you are causing congestion. Okay. So that is what back pressure is. Next is sorting and randomization. That is, these are the tasks that you generally do at the input ports or the samples that are arriving at the input ports. Okay, so for certain switch fabric, you can sort the input, you can randomize the input to reduce the internal blocking. We will see how this works in the next few slides. And then we have parallel switch fabrics. So instead of having only a single switch fabric, you can have parallel switch fabrics working together, and that will increase the effective switching capacity by connecting the different input ports to the output ports with multiple parallel switch fabrics. Okay, so these are different ways of dealing with blocking. All right, now yes. So we've already studied about the three different generations of packet switches in the last class on routers. So I had told you that those are different generations of routers, where the routers had changed the way in which the basic packets that are arriving will move from the line card, one line card to another line card. Okay, and the line card is of course having the corresponding input and output ports with it. So when I was talking about it, I also talked about the fact that these buses or the common mode of transfer between the different line cards and the processor, those were actually different formats of the switch. Okay, so we did not get the concept of switch before the third generation. So in the first generation we were simply using the PCI bus. That means some mode or some medium that is a common shared medium being used by the different line cards to support the transmission of data from one line card to another line card. That means from one input port to another output port. Okay, so I will not get through these different types of switch fabrics. We have already studied about this. Instead, I will get to a different. Okay, let me see about it. This is about second generation switches. This is the third generation switch. So I'll start with the third generation switch. You already know what the second and first and second generation switch does. Or if you want, I will just go through like one slide each, one line each in that case. Okay. All right. Just give me a break for 1 minute. I'll just drink some water and then I'll restart again. Okay. Okay. Am I audible? Hello?
Yes,
Yes,
ma'am.
ma'am.
Okay, okay. All right. So let's get to this once more. So in the first generation switch, we had a PCI bus being shared between the different input and output ports. And when it comes to the second generation switch, we had shown that there's a shared bus, a separate shared bus that was responsible for moving the packets from one input port to the output port. Okay, so that was for the second generation switches. And even with that, we were basically facing the problem that because it is being shared by different line cards, it will be limited by the capacity, as well as it will also limit the number of line cards that can actually um, use that bus. Okay, so this is the case for second generation switch, and this is how it looked like. All right, so we had, when we were talking about routers, we had different forwarding engines here at these at these line cards. That means most of the task was getting distributed at the line cards, and this concept was further taken up by the third generation switch. Okay, so this is what our second generation switch looks like. Now we come to the third generation switch. Okay, so the third generation switch, we came to this idea that instead of having a bus, let's have a kind of switch fabric which will give various paths or a number of paths from the input to the output. Okay, so that's what we called as a switch fabric. And just now, up to the last slide, last few slides, we have just seen that how many different kinds of switch fabrics can be there, and we have studied for that for circuit switches. Okay, and now we are going to study that, for packet switched network. Okay, so yes, we do have a control processor here. As you can see, we have input line cards, output line cards. Of course, if you remember the class, the beginning of this module, we do consider this as a folded scenario. This is shown unfolded. If you fold it, then it will become one line card having an input and an output port. Okay, so this is the third generation switch. We have an input line controller, we have an output line controller at each input and output port, and there is a control processor in between which does its task of telling that where should the packet be moved to. Okay, so this is how it works. Now let's get to different types of switch fabrics. Okay, but before that, what should be the features for that switch fabric? It should be self-routing, right? It should be a self-routing switch fabric. The output port will be a point of contention, as we have already seen that output blocking will be there in case of datagram switches. Okay, so in that case, we would need to arbitrate the access to the fabric. That means you need to schedule the access to the fabric in such a way that you have minimum amount of output blocking. Okay, now next is that this does have a potential for unlimited scaling as long as we can resolve the contention for the output buffer. Okay, so this is how the third generation switch should have the features, the important features of third generation switch. Now let's get to different switch fabrics. Okay, so this is just how what switch fabrics are. Let me not get into this. Simplest one we have already studied, that is a crossbar switch. It can be used for the packet switch circuit also. Now, for packet routing, the cross point is active long enough to transfer a packet from one input to an output. Okay, if the packet size is known and if the arrival packet is known, then it is great. Then you can always compute the schedule in advance and you will have reduced amount of contention. Okay, it will more or less work as a circuit switching, but it actually helps you out in having very much reduced contention if you're having fixed size packets and you know that how those packets will arrive. If these are not there, or if you have variable size packets and you do not know the arrival pattern, then on the fly through your switch fabric, when the packet needs to move, you need to find the schedule. Okay, or you need to compute the schedule so that the packets can be moved from one input port to the corresponding output port. Okay, so that is a complexity that will come into picture. Now let us see that how do we work with this. So this is one kind of switch fabric, okay, which is known as a Banyan switch. Okay, so let me see whether my pen works here or not. It's not working. Let's see. No, it's not working on the PDF. Okay, Um, let me see it in this way. Just a second. Should anyways, I'll try it in another way. Okay, so look at this picture of a Banyan switch. You have 2 cross 2 switches here. Okay, so you have 2 cross 2 arrays in 3 different stages, and they are connected with each other. Okay, in this way. All right, now these inputs and output ports are represented in terms in binary. All right, 000 to 111. So these are the input and output ports. Now, how does any input that is entering this switch, how does it move to the corresponding output port? That's what we need to find out. Okay, so Banyan switch is said to be the simplest self-routing recursive fabric. Okay, so how does it work? Of course, if you need it to be self-routing, then you need to give the address every time. How will you give the address? Of course, your packet has to be tagged with it, but every time reading the IP address would be pretty difficult. Okay, so what you do, you just tag the packet with the output port number in binary. Okay, you've seen that we have tagged the input and output ports in binary in case of the Banyan switch. Okay, now the packets that are incoming, that will also be tagged with the output port number in binary. Okay, and of course we have seen that it is made up of 2 cross 2 switches, and the fabric will need n stages for 2 power n outputs with 2 power n minus 1 elements in each stage. Okay, so why does this work? It works because each switching element at the ith stage will look at the ith bit to make a forwarding decision. Okay, again I will repeat this. Each switching element at the ith stage will look at the ith bit to make a forwarding decision. So if the switching element is at the first stage, okay, so that means it will look at the first bit of that output port. So your packet is tagged with the output port number in binary. So what will the switching element do? The switching element will see that at what stage of this switch it is. It is in first stage, suppose. So it will check the first bit of that tag that the packet is tagged with, and then it will make a forwarding decision. If the switching element is at the second stage, then it will check the packet's second bit to make a forwarding decision. Okay, now let's see how this works. All right, so please remember this is a 2 cross 2 switch. Okay, so this is tagged as 0, and the upper this line is tagged as 0, and then this line is tagged as 1. I'm sorry, my pen is not working on this one, otherwise I would uh, show you by writing on this. If you do not understand, please let me know. See this input line, somehow I think you can see the hand symbol. This input line will be entering or allowing all the packets which have their first bit as 0. This one will allow whatever packet that is arriving with first bit 1. So for all of these switches, this upper line will represent or will allow any packet which is intended for 0, okay, which is having the binary bit 0 at that stage. This is for 1. Again, this is for 0, this is for 1, this is for 0, this is for 1. Like that, for each one of them, it works out. So that is fixed. All right. Now let us have an example here. So at this particular input port, some packet has arrived that has the destination of 010. That means the output port is 2. and for this the output port is 3. Okay, so this is an input port which intends to go to output port 2. This is an input port where a packet has arrived which intends to go to output port 3. Alright, so what do we know in Banyan circuits? We convert the output port number in binary. Okay, and what do we know? The switching element will check that which stages it is in. If the switching element is at the ith stage, then it will check the ith bit of this tag. All right, so it is checking the ith bit. It is the first stage. It is checking this first bit here, and it is 0. All right, so it will be sending it over this line. So now this tag is here, that is 0, 1, 0. Okay, now this is the second stage. Okay, so this switch fabric is at the second stage, so it will check the second bit. So second bit is 1, so that means it has to be moved through this line. So that is 0, 1, 0. Second bit is 1 here. This is the second stage, so this goes through this line. Okay, now when it enters here, this switch will check that okay, it is the third stage. So let me check the third bit. What is the third bit for it? That is 0 here. So that means it will send it through this one. Okay, so now you are getting 0, 1, 0 here, and it is exactly that output port, that is 0, 1, 0. So it is reaching its corresponding output port. Okay, similarly for this one, 0, 1, 1, which is intended to output port 3. So what is the first bit? That is 0. So it goes through this path, 0, 1, 1, reaches the second stage. In the second stage, the switch fabric checks the second bit, that is 1. So sends it through this line, below line. Then again, it goes through the next switch fabric, that is, going to check the third bit, and then it checks the third bit, which is 1, and then moves it through this one. Okay, so this is how this Banyan switch will work. Okay, I hope that this is clear. If not, I can explain again. So now I do have a question. So will this kind of a circuit be blocking or non-blocking? Okay, can this kind of a circuit be blocking? Any answers to this question? Can there be a scenario when you are having output blocking? Was this clear to everybody? Banyan switch, give me a yes or no answer. Yes?
Yes, ma'am.
So then I am asking that you have seen now that how the packets are being moved to the corresponding output ports. So I am asking that can there occur any scenario where there will be output blocking? That means you do have the input ports, packets at the input ports, but the output port is not available to send. Can that scenario occur?
Ma'am, if two packets have the same output destination, is that possible?
Should be possible. What do you think?
Then blocking is possible.
Okay. All right. Is there anybody who thinks that blocking is not possible? All right. So I will keep this question then. Anyways, I have another slide here, so that doesn't make much sense. So anyways, we do have blocking in case of Banyan switches. Okay. So yes, of course, if the two packets are intended for the same output port, and the paths are somehow contending with each other, so in that case, if they are at the same time asking for the same output port, then of course there will be a contention in that case. Okay, so there will be blocking in this case. Now how do we How do we avoid blocking in case of a Banyan switch? Okay, so one way you can think of, we have seen that there are many ways of avoiding blocking. So one way you can think of is, okay, let us have buffers. Okay, so buffers at each element becomes again, this is again becoming expensive. Okay, so and also even if you have buffers, you cannot guarantee that you will not have any loss. What if you have too many packets arriving as compared to the size of your buffer? So you cannot say that there will not be, or your blocking will be totally avoided. You cannot say that in that case. So buffers is one way to avoid, but it cannot completely avoid the scenario of having, blocking in this case. Okay, so what can we do? Okay, instead you can check that how the input is arriving, and you can probably make changes in the input itself. That, let me change the input in such a way that if there is a contention, then they will avoid the amount of contention, like we have already studied in circuit switching, right? How can we use that in case of Banyan switches? Okay, so there are three phase schemes which are used in this case. One is, that is, send the request, inform who are the winners. That means the winners will be the ones for whom the path is available, and then you send those packets, keep the other packets. That is one way. Another is, that is, you sorry another way is, that is, you use several banyan fabrics in parallel. Okay, and you intentionally misroute and tag one of a colliding pair and divert those tag packets to a second Banyan stage. Okay, so that means whatever contended packets you are having, you are simply routing them to different Banyan switches which are at different stages. Okay, this will reduce the amount of contention that you are having. All right, but what will happen? This will be expensive. You will have to have more number of Banyan switches. That is one. Then next is what, you are intentionally misrouting the packet to the next stage, right? So that will, that will change the ordering of the packets. So again, you have to reorder the packets at the output port. Okay, and what is the one more need that you are having? That the output port buffers, now that you have several switch fabrics in parallel, your output port buffers have to run much faster as compared to the input port, because you are getting a lot of inputs at the same time, and you have a lot of large number of switch fabrics that are staged in parallel. Okay, so that is the issue that you have when you are putting Banyan fabrics in parallel. And the other one that we have already seen, that if you basically just find out which packets are the winners, and then let them use the fabric for that point of time. So these are the issues that we have. So can we improve this? So one of the methods that we had studied while seeing that, how can we avoid blocking, there was one more method, that was sorting and merging. Okay, so now what we are trying to do here is, we are trying to sort the input. Okay, so we are basically changing the order in which the packets appear at the input port. How are we changing the order? We are changing the order by sorting it as per the output port. Okay, so this is the input that you are having at the input ports. Okay, cross means no inputs at this point. Excuse me. So this is the input that you are having. You sort this and you get this, the sorted input. Okay, now here you can see that there are two input ports, or there are two input ports which have packets intended to the same output port. Okay, 011, 011. So what you do, you remove the duplicates. So you removed one of the duplicates. Now you're having this as the entire input tuple. Now you shuffle this, okay, so that there is no intersection among the paths 2, and then you have shuffled this. So now this can easily move through this particular network. Okay, so this is what this is how you can use or this you can use as at input ports, so that you have reduced amount of contention in case of Banyan switches. Okay, so how do we do this? We need a sorter, we need something to shuffle the inputs, and we need something to remove the duplicates, and we call it as a trap network. Okay, now once you have done this, we need merging. Okay, so merging networks are what? A merging network of size 2n takes two sorted lists of size n as inputs and creates a merged list of size 2n. Okay, so if you sort the inputs and you divide it, sort the lists of size n as inputs, and then you want them to merge, then you just get the amount of merged lists. Very simple as it can get. So there can be different ways of merging networks. Okay, so suppose you take one of the ways is like, suppose you take two n-sized merging networks. So if one of them merges all the even elements of the two inputs, the other one can suppose merge all the odd elements. Okay, so this depends on how you actually want your merging network to work out. Okay, so then whatever the output you are getting from the merging network or the merger, you simply hand it to a 2x2 comparator, and then that will give you the particular output. Okay, so this is how your merging network will work. Let me show you how, if you put everything all together, your Batcher Banyan, we call it as a Batcher Banyan because you have all of these parts here and the sorting is happening as a batch here. So what we do, we have a sort network, we get the inputs here and we sort the inputs, then we remove the duplicates with the trap network, then again we shuffle this, and then we send it to the Banyan network so that we can avoid the amount of blocking. All right, so this is how your Batcher Banyan looks like instead of the simple Banyan network, that is a simple Banyan fabric that you were having. And this is the last slide for this class today. I know that I have extended the time by a minute, so I'll quickly go through this. So of course there is an effect of packet size on switch fabrics. Okay, that is why ATM switches, in order to remove this, they have same size packets. Okay, but how can we avoid this issue? We can actually have fragmentation and reassembly being used here. Okay, so if you fragment a variable size packets to the same size packet, to a fixed size packet, and then send it and then use it over your switch fabric, and then in the end you reassemble them, then it is fine. Okay, so even if you are having variable size packets in your datagram switches, you can actually use the concept of fragmentation and reassembly, or you can build an asynchronous switch fabric, which is pretty complex. So you can use fragmentation and reassembly to avoid any issues that arises with variable size packets. Okay, so this ends this module for switch fabrics, and this also ends today's class. All right, so I will stop the class here. If you have any questions, you can ask me. Okay.